Jai Hind students. Now today's topic we are again going to continue with the previous topic, that is free fall. So what is our next topic? Free fall for today. Some part of the free fall we have already discussed, that what is free fall, what do we call the acceleration of a body falling freely towards the earth, that we call acceleration due to gravity and symbolized by small g. And then we talked about the reason behind acceleration and all. This was in the previous video. Now continuing with the same free fall, we are going to add something more about free fall. And today's class is going to be very interesting, very knowledgeable for you, because whatever we are going to understand, that theoretically we will understand no doubt in the class, but with the help of videos, we are going to add flavor into that. That means the video required for that, the resource which we have arranged for you is really going to be very interesting for you, because in real life arranging free fall is not possible. But this video which I am talking about is arranged by NASA in one of his experiments by a scientist, and then we proved again the fact related to free fall. So what is that fact and how can we verify this by watching this video? So that we are going to discuss in today's class. Okay. So wait for the discussion first and then we'll go for videos. Okay. So first of all, derivation of formula for G. Then we'll go to formula for G at moon also we'll try to, because moon is our next neighbor. So we are going to find out the formula for G also there also. And one thing you should understand, that you must be knowing also, that on the moon we get natural free fall. Because I know you can guess now why this natural free fall is available there, because on the moon there is no atmosphere due to poor gravitation. That is, here also the gravitation plays a vital role. That earth has a very good amount of gravitation, so it can hold the atmosphere. But if you leave, suppose you are carrying 5 liters of oxygen and releases on the moon surface, do you think that it is going to make atmosphere? No, because moon's gravitation is not strong enough to hold that volume of gas, so it will escape into the space. So that's why atmosphere is not present there. But on the other hand, if atmosphere is not there, so you can easily guess that there we can observe free fall. But obviously it will be different free fall than on earth, because earth's gravitational pull and the moon's gravitational pull is different. Okay, so that we are going to discuss in our discussion. Then comparison of G at earth with the moon, that we are going to compare with that. Okay, that how much G is there at earth and what is the experience of G at moon. And then one very interesting, that effect of G on human being. Like if we increase or decrease the value of G present on earth, then what kind of difference we can perceive. So that also is a very interesting topic we should understand. Okay, so without wasting too much time, we are going to derive the formula for that acceleration due to gravity. Okay, it's a very simple. So suppose we have to derive this formula, where we can get the value of acceleration due to gravity, that is G, by capital G into mass of the earth upon radius of the earth square. Okay, so now here very weird thing we will observe, that we always find out the acceleration due to gravity for a free falling object. So here you can see in this formula, the mass of the free falling object is nowhere, because earth produces acceleration with the help of gravitational pull on that object in the absence of air, that is during the free fall. But nowhere you can see that mass of the free falling object is present in the formula, and that is only the amazing thing. The free fall for which we are studying, the mass of that object is nowhere. So that is not easy to believe by students. So we are going to prove theoretically as well as in the visual form also in your video. Okay. So first of all, we are going to derive this formula theoretically. Okay. Now suppose this is earth of mass m, suppose, and radius is r, and near earth's surface some object is falling towards the center by the gravitational force F of mass small m. Okay. Now this is accelerated. Now according to Newton's second law, we know that force is equal to mass into acceleration. That is Newton's second law. Okay. Now from that we can derive that A is equal to force by mass. Okay. Now in the world of gravitation, A is actually representing the acceleration due to gravity. So can we replace A by G? Because here we are talking about acceleration due to gravity. So here acceleration is small g. Now for force, we can find out the value of gravitational force only, because here the accelerating force is no other than gravitational force. So the F which we are calculating here is actually the value of gravitational force. And according to our knowledge of formula for gravitational force, we can replace the gravitational force value by capital G into mass of the both object, that is mass of the earth into mass of the falling object, upon RE square. Suppose we are taking that. Okay. Now dividing by mass m. Value of gravitational force by this value of mass of the falling object. So what we are going to get? That we are going to get capital J into mass of the earth into the mass of the falling object divided by RE square. And since it is taken, this is taken as numerator, and so 1 will be considered here, so it will reciprocate by 1 by m. Now this mass of the free falling object and this mass of the free falling object, since they are same, so they are going to get cancelled. Now you can see here the mass of the free falling object is getting cancelled, which is not easy to believe, but it is the fact that free falling object, when accelerates, the mass of the free falling object itself does not play any role. So what does it infer? That whether it is a lighter object, that means having less mass, or an object which is having very high mass, if they are released from the same height, it will accelerate in the similar manner, and if they are released at the same height, they will collide with the surface, with the ground in the same time. But when we see the things falling in our real life, you will see that a lighter object and the heavier object, there is a quite different. Like as I will show in the video, when I will drop a lighter object with respect to a heavier object, you will see that lighter object is falling slowly and the heavier object is going faster. That means acceleration is different. In the same video, you will see that two almost same heavier object having high density and less surface area, when we release, they also falls almost with the same in the same time. I have said almost, but they are also different, but due to very small interval of gap, our eyes cannot recognize that. But there also there is a difference found in the falling, in the value of acceleration, because air friction is there, drag is there, and drag matters for those objects having large surface area, less density. So lighter object, that's why it has greater experience of drag, and that's why it floats like kind of thing, it falls in the floating kind of thing. Dense material and less surface area, then the effect of acceleration is almost negligible, drag is almost negligible, but that doesn't mean that it is going to allow you the pure free fall. There are also differences there. So you will see in the video, you will compare that. But when we do the comparison of free fall of any two objects, whether lighter or heavier, with this formula we can conclude that mass of the free falling object does not matter. So that was all about derivation of formula. Find the value of formula for G at moon. So do you think that we are going to apply this same formula? No. But the relation will be same. Suppose I am taking acceleration due to gravity on moon of the same object. Okay. So what we will see? Capital G will be capital G, because capital G is a universal constant. Then do we take mass of the earth, or should we take the mass of the moon? Suppose this is moon and this is the radius of the moon, and the same object has reached to moon. So here the acceleration due to gravity, here the mass will be taken of moon. So mass of moon upon. Do you think we should take the radius of the earth here? No. because we have reached to moons. According to moon we have to take. Suppose we are reaching to Jupiter, so we have to take radius according to Jupiter and the mass of the Jupiter. So that accordingly. So Rm square. So this is the expression for acceleration due to gravity on moon only. But only the mass and radius will be changed. G will be everywhere common. Suppose we calculate for Jupiter, so we will take capital G there also, mass of the Jupiter upon radius of the Jupiter. So anywhere when you go, you will take the mass of that object, heavenly object, and the radius of that object. Okay, average radius. So this is the expression for acceleration due to gravity on moon. Now, so we have till now we have discussed these two topics. Now we are going to compare comparison of G at Earth with respect to moon. So suppose I am comparing the acceleration due to gravity here with respect to, so I am giving name GE and here I am giving name GM. Okay. So if we compare, so these are two expressions. So if I compare these, so suppose GE, GM upon GE I am taking. Okay. So for GM I will take capital G into mass of the moon upon radius of the moon square upon, for GE I will take capital G mass of the earth, that is the expression, upon radius square. When you reciprocate it, what are you going to get? Capital G into mass of the moon upon radius of the moon square into radius of earth square upon capital G into mass of the earth. So here you can see capital G is common. So they will get cancelled, and finally when we take a ratio, the mass of the moon upon mass of the earth, that means these two we have taken together, mass with mass, and then I have taken radius with radius. So radius of the earth upon radius of the moon square. Now when we get this values, so suppose I have taken a rough values for mass of the moon like 0.73 into 10 power 24 kilogram, and the mass of the earth, that is 6 into 10 power 24 kilogram. Then radius of the earth 6.4 into 10 power 3 kilometer, and the radius of the moon almost 1.738 into 10 power 3. Now when we place these values, substitute these terms by their values, we are going to get a relation almost 1/6. Okay, so acceleration due to gravity has a relation of 1/6. That means the acceleration produced by moon on any object on its surface is 6 times weaker than the acceleration produced by earth on any object on the earth's surface. So that way you can find out the relation of acceleration due to gravity on moon to the acceleration due to gravity of any object, same object on the earth. Almost it will be 1/6. So around it is 9.8 is here. So you take out 1/6 of the 9.8, you will get the value of acceleration due to gravity present on moon. So in this way you can compare any two places, any two heavenly object, and you can compare the acceleration due to gravity present on these two heavenly objects. So we can have comparison of, we have done comparison of G at earth with the moon. Now finally, what is the effect of G on human? We, from our childhood days, we live according to the gravitational condition present on earth. So we almost live with a value of 9.8 meter per second square, which is found almost everywhere on the earth's surface averagely, because from place to place it varies. So how does it vary? That value of acceleration due to gravity on different parts of the earth, that we'll discuss in the next video. Now we are habitual of living in the acceleration of value 9.8 meter per second square. Now what will happen if we reduce this acceleration due to gravity, or if we increase it? Is it going to affect our physiology? Is it going to give any stress to our body? Yes, it plays an immense role in affecting your body. Suppose we talk about astronauts, which they live in space, so they have to live in zero gravity, and living in zero gravity means acceleration due to gravity is almost zero. So that means living in that situation is not at all easy. So that's why when astronaut is supposed to be sent in the space, on the earth surface with the help of special kind of aeroplane, they are provided practice to live in zero gravity. We can create zero gravity with a special technique. So in zero gravity they are trained accordingly, because they have to live in space in zero gravity. And believe me, when you go to zero gravity, that means where the acceleration is almost taken zero, so you will start vomiting. It will have all the effect on your body, your heartbeat, your muscular expansion. This all will take place. So it's not easy to survive in zero gravity. So if you decrease the value of acceleration due to gravity, that is also going to affect. Now if you increase the value of g, that also is going to affect your body. In case of, if suppose you are increasing the value of g to 4g, 5 times of g, 9 times of g, then you can collapse even. You can be unconscious around 5g, and if you reach to 9g or more than that, you can even collapse. So that's why the fighter pilots, they have a very hard training. When they are flying the fighter planes, sometimes there will be a sudden drop of the fighter plane. In that situation, the value of g increases very high to 9g even. So if the body is not capable of tolerating that, how can they survive? They will be unconscious. So they are trained astronauts, fighter pilots, because it's not easy to survive either in high value of g or in the low value of g. So that is the thing. So it has a great impact on our human body. Okay, on our enzymes, on our hormone secretion, everything gets affected, whether you live in zero gravity for a long period of time or you live in higher value of g. So both are going to affect our body. So that is a great effect on our body. Now I hope you have got something new from this class, and observe all the videos and try to find out, try to open up your mind that, and try to believe that yes, the mass of the free falling object doesn't matter. But again, don't get confused that pull of the gravitational force matters on the mass of the object, free falling object, the pull, the gravitational force. But acceleration produced by that gravitational force during free fall is not dependent on mass of the free falling object. Acceleration is independent of mass, but yes, force is dependent on mass of the object. Okay, so have a nice class, enjoy the class and keep learning. Thank you very much.